Alright class, let's continue talking about NMR. And again, what NMR is nuclear magnetic resonance. I have no idea who comes up with these names. Now, last time, what we talked about, we said you have carbon NMR and you have proton NMR. And when you have proton NMR, when you get your NMR spectrum, it's going to be usually from 0 to 12. 0 is just a TMS peak. Basically, this is our reference peak, and everything else is measured against the reference peak. And then we call this ppm. These are chemical shift, and we talked about when you are upfield versus you are downfield. So far, so good. Okay. Now, what we're going to go over, we're going to go over these chemical shifts and how we have characteristic chemical shifts. Before I go over that, I want to remind you one more time that when we have an NMR, for each set of unique protons, we are going to have a signal. So for each set of unique proton, we are going to have a signal. I want you to keep that in mind as I'm doing practice problem and going over NMR. Alright, so the first thing that you are going to do when you look at an NMR, you're going to look at chemical shifts. Okay, so number one, the first thing we're going to do, we're going to look at chemical shifts when we look at NMR. So far, so good. Now, I attached this handout for you guys. So you have this handout. And I'm going to go over this handout in a second. But before I go in over this handout, I want to talk about these chemical shifts a little bit more. So, we are looking at the chemical shift. You get an NMR spectrum. The first thing I want you to do is to look at those chemical shifts. And we said that chemical shifts, these are in ppm, parts per million. Okay. Now, we are talking about proton NMR. So what you are looking at hydrogen. I need you to remember that what we're looking at, we are looking at hydrogens. Because we're talking about proton NMR. So what you're looking at hydrogens. Don't forget that. Don't forget the little things. All right. You ready to do this? Okay. Now, if I have an aldehyde, and R is just, doesn't matter, a bunch of carbons. If I have an aldehyde has a hydrogen. Do you agree? This hydrogen is going to show up on about 9 to 10 ppm. Okay, so if you look at the NMR spectrum and you see a peak around 9 to 10 ppm, what are you going to say? You're going to say, oh, I have an aldehyde. Now, let's say you have a carboxylic acid. Carboxylic acid has a hydrogen. Because again, remember, we're looking at proton NMR. We're looking at hydrogens. Now, that hydrogen is going to show up, have a signal between 10 to 12 ppm. So if I see a signal at 12 ppm, I'm going to go, oh, I have a carboxylic acid. That's from the hydrogen on a carboxylic acid. And one more time, what is R? R just doesn't matter. It's just a bunch of carbon, the rest of the carbon chain. The hydrogen is what I'm looking at right now. Now, when you have a benzene ring, which is such a common functional group, the hydrogen on a benzene ring are going to show up between 6.5 to 8 ppm. It's pretty good. So this is why NMR is so beautiful. You look at NMR spectrum. If you see a peak at 9 ppm, you go, oh, aldehyde. You see a peak at 10 to 12 ppm, you go carboxylic acid. You see a peak between 6.5 to 8 ppm, you go, oh, I have a benzene ring, which is kind of cool. Now, if you have an OH, or if you have an NH, I'm just going to put R for here too. Now, OH and NH, those have hydrogen bonding, right? Now think back to the IR lecture for me. Let me see how much you remember, how much you pay attention to my lecture. Think back to the IR lecture. When we were talking about the IR lecture, we said when you have OH or NH and those have hydrogen bonding, they're very polar bond. What happened to the signal on an IR? You would get a broad peak. Remember that? You would get a broad peak on an IR. Now, this is almost the same concept here. When we have a chemical shape for OH and NH that have hydrogen bonding, you are also going to get a broad peak. You're almost going to get a bump. Okay? And they show up between 1 to 5 ppm. So there's a huge range they could show up, but they are going to be broad. So you are going to have a broad peak. And the way I like to look at it is almost like a bump. It's going to be like a little bump. Other signals are very sharp, but when you have OH and NH, you have a little bump. So again, I'm going to show you all of these on a spectrum. So when you see a little bump, you go, oh, I have OH or I have NH. So far, so good. Okay. And this handout that I have here, and you have a copy of it too. Again, this is what is going over. If you have a benzene ring, 6.5 to 8. If you have an aldehyde, 9 to 10. Carboxylic acid, 10 to 12. I'm just going to go over each one in detail because I want to make sure you really understand this. So far, so good. Not too bad. Okay. Now, let's continue with this. If you have a hydrogen that is attached to a carbon that is an sp2 carbon, it's a double bond, that's going to show up between 4.5 to 6 ppm. Okay? Now, if you have a hydrogen that is attached to a carbon that is sp3, so it's all single bond, this hydrogen is going to show up between 0.9 to 2 ppm. Okay? And again, I know I keep repeating myself, but I need you to really pay attention to this, is that proton NMR is for hydrogen. So what we are looking at hydrogens, right? We are looking at hydrogens. Don't forget that. I need you to keep that in mind. So far, so good. Okay. Now, let's go over this for a second. So here I said, if you have an sp3 carbon and a hydrogen is attached to an sp3 carbon, then you're going to have about 0.9 to 2 ppm. Now, when is it going to be 0.9 and when is it going to be around 2? So let's go over that right now. So here is the deal. The more alkyl substitute you have, the higher the chemical shift. Now, what does that mean? Here's what I mean by that. Let's say over here, again, we are looking at this hydrogen, right? Let me draw this part out. Let's say the first carbon is attached to two other hydrogen and a carbon. Let's say we're attached to one hydrogen and 2 carbon, and here we're going to be attached to carbons. Okay, now what am I trying to show you here? Here's what I'm trying to show you here. Okay, so let's look at this one right here. If I look at this one right here, first of all these hydrogen, this one, and this one, they are going to have one signal. Do you guys agree? All of these are going to have one signal because they're all equivalent to each other. I have one set of unique hydrogens. Okay. Now, this is most likely are going to show up around 0.9 ppm. Okay. Now let's come down here. These two hydrogen are going to give rise to one signal, right? They're one set of unique hydrogen, they're equivalent to each other. Now, this carbon is attached to two carbon. What did I say? The more alkyl group you have, the higher the chemical shift. So what do you expect this to be? This is going to be a little bit higher chemical shift. Okay, now over here, I have this one hydrogen. Okay, now this one hydrogen is going to give rise to one signal. Now this hydrogen is attached to a carbon, and this carbon is only attached to other carbon, right? So this is going to make the chemical shift to be even larger. So this is going to be around 1.7 ppm. All right, so this is what I mean by that. So you have sp3, so you have a hydrogen attached to a sp3 carbon. So we're looking at the hydrogen attached to an sp3 carbon, right? But again, this sp3 carbon, you can have one carbon attached to it, two carbon, or three carbon attached to it. Now, depending on that, the chemical shift is going to be different. Now, if that carbon is attached to more alkyl group, the chemical shift is going to be higher, as I showed right here. So far, so good? Okay, so hopefully you guys are following me so far. I'm going really slow. Hopefully this is helping you understand it. Now, here's another sp3 situation that we could have. We could have this again, and I'm looking at this hydrogen because NMR, we're looking at proton NMR, we're looking at hydrogen. Now, in this case, one of the substances, one of the things that are attached to carbon, one of the substituent is Z, and what Z is going to be an electronegative atom. It's going to be nitrogen, oxygen, or halogen. Okay. Now what's going to happen? What do you think? Now what do you think is going to happen? I want you to answer this. I know I can't hear you, but I really want you to answer this and think about this. Now, here's a hint I have for you. When we talked about what is going to show up upfield, what is going to show up downfield, we talked about this. So think about this for a second for me. If I have a hydrogen that is attached to a carbon that has an electronegative atom attached to it, now what does that mean? What's going to happen to the chemical shift? Okay. So if you remember, we said when you are attached to an electronegative atom, which is the case here, the electronegative atom is going to pull all the electrons, or most of the electron, toward itself. So hydrogen here has an electron cloud that is going to protect it, shield it against the magnetic field. But if I have an electronegative atom here, like oxygen, nitrogen, halogen, that they want an electron, they're going to pull the electron this way. If they pull the electron this way, then the hydrogen is not going to have as good of a shield against the magnetic field, so it's going to see the magnetic field more. It's going to feel the magnetic field more, so the chemical shift is going to be higher. So far, so good? Okay. So what the chemical shift is 2.5 to 4 ppm. So far, so good? Okay. Now, let's go over this. If the Z is oxygen versus the Z is nitrogen, which one do you think is going to cause a larger chemical shift? Think about this for a second. Oxygen versus nitrogen. Which one is more electronegative? Hopefully you remember your Chem 1A, and you're yelling at me right now, duh, oxygen is more electronegative. Okay, beautiful. Now, oxygen is more electronegative. So if oxygen is more electronegative, do you agree it's going to pull even more electron this way? So this hydrogen is going to be even more electron cloud deficient. So it's going to fill the magnetic field more. So the ppm is going to be larger. So far, so good. Again, these are rough numbers, but usually when you have oxygen, that hydrogen will show up around 4 ppm. But when you have nitrogen, it would be around 3 ppm because oxygen is more electronegative. Yeah? Okay. Beautiful. Really, really, really nice job. All right, we are almost there. We're almost there. You guys ready for the next couple ones? We're almost there. All right. Now, the next thing is, what if I have an SP? I still have an SP. What if I have a SP carbon? I have a triple bond, right? So we went over sp2, we went over sp3. What if I have a sp? Now, where would that show up? That would show up around 2.5 ppm. That would show up around 2.5 ppm. So far, so good. Okay. Now, one last one I want to talk about. What if I have a carbonyl group and I am looking at the hydrogen over here? This is the hydrogen I'm looking for. So the hydrogen is attached to a carbon that is attached to a carbonyl group. Now, before you get confused, remember, if the hydrogen was directly attached to a carbonyl, that would be an aldehyde, and this is a chemical shift. If the hydrogen was attached to an oxygen that was attached to a carbonyl group, so it was a carboxylic acid, this was a chemical shift. Now what we're talking about, what if the hydrogen is attached to a carbon and the carbon is attached to a carbonyl? What would that happen? Again, this is kind of the same idea because oxygen is electronegative. So there's a pool of electron that is going this way, right? So because this carbon is not directly attached to an oxygen like it was here, so the chemical shift is going to be a little bit lower. Because here, when the carbon was directly attached to oxygen, a lot of these electrons are being pulled this way, so then that makes this one to have to be really electron cloud deficient. And then you would have a high chemical shift. Versus here, this carbon is attached to a carbon that is attached to an oxygen. It's kind of like not having a friend, but having a friends of the friend, right? So because of that, so it's not as high of a chemical shift as the case before. So what we have around here is 1.5 to 2 ppm. Sounds about right. So far, so good. Okay, and I'm going to make a note of this again. This carbon, the carbon bonded to hydrogen is not directly attached to oxygen, right? Because it's attached to a carbon, then the carbon is attached to an oxygen. So because of that, the ppm is going to be lower, versus here, this carbon is directly attached to an oxygen. Yeah? You guys feel pretty good about this? Okay. So this over here that I have given you guys, this one down here is carbon NMR. Don't worry too much about it. But here is what I want you to look at. We almost went over the entire thing. So you should have this in front of you. I kind of like this. You should definitely have this in front of you as we are going over different NMR spectrum. All right, so that's the first thing, chemical shift. Let's go back to the sample spectrum I have given you. Okay, and you knew this was IR and this was proton NMR. Now let's look at this proton NMR now that you know chemical shifts. You see 1, 2, 3 peaks. Okay, again, these are all important. I see 1 peak, 2 peak, and 3 peaks. So I have 3 peaks on the NMR, which means I have 3 sets of unique protons. Now, one of them is about, 1.3 ppm. One of them is about 2.0 ppm. And the other one is about 4.0 ppm. So, and we haven't finished talking about NMR, but I feel like you can already know so much from this. So you have a peak over here at 4 ppm. What's going to cause it to be at 4 ppm? If you're going to be downfield, that's considered kind of downfield, is then the carbon that is bonded to the hydrogen should be directly attached to an oxygen, right? Okay, so we have that. We probably have a hydrogen that is attached to a carbon that is attached to an electronegative atom, possibly hydrogen, because again, don't forget, possibly oxygen. Don't forget, I give you the formula over here. Okay, 2.0. That's interesting, right? Because we know that there is we know that over here there is a carbonyl. There is a carbonyl peak. So, okay, so we can kind of guess what is going to be this one over here, right? Because if you have a carbon bonded to the hydrogen and this carbon is attached to a carbonyl group around 1.5 to 2 ppm. Okay, so that sounds good. And this is around 1 ppm. So this is just carbon-hydrogen peak. So far, so good. Okay. Again, I'm not expecting you to figure out the structure yet. I just want you to have a feel for this. That's all I want you to do. I just want you to have a feel for this. So here, right now, all I want you to know, these are 3 peaks on the NMR. One is downfield. So this one I have it is probably in the carbon is attached to an electronegative atom. And then over here, the carbon that is attached to the hydrogen is probably attached to a carbonyl. And then this one, I have my CH group. So far, so good. Okay. All right. So hopefully this helps you to kind of get a feel for what NMR is. The next thing to look at when you're looking at NMR is integration. So when we were doing the practice problem just now, okay, this was great. You figured out the chemical shift and we got a lot of information out of it based on the chemical shift. You were probably asking me, even though I can't hear you, it's like, hold on a second, what are these numbers? It says 3 hydrogen, 3 hydrogen, 2 hydrogen. What are these numbers? Well, I'm so glad you asked. Those numbers are the integration. Those numbers are the integration. By the way, you have this handout, so make sure you have it in front of you if you can't see my screen that well. All right, so these numbers over here, so we know the chemical shifts, that these numbers are the integration. Now let's go over what does it mean, what does integration mean. So here is the deal with integration. The area under an NMR peak, the area under an NMR signal is proportional to number of absorbing protons. The area under an NMR signal is proportional to the number of absorbing protons. Now, what does that mean? So, basically, to summarize this, the height of the peak is proportional to the area under. So the height of the peak is proportional to the area under, and that is proportional to the number of hydrogen that you have. Okay, so the height of the NMR peak is proportional to the area under the peak, and that is proportional to the number of hydrogen. Now, the NMR spectrometer automatically calculates this and plot it for you and give it a ratio. Okay? So again, this is like where I'm going to tell you guys, you kids have it so easy, because back in the days, the NMR spectrometer wouldn't calculate this and then give it to us. We would have to do it ourselves to figure it out. This is what I go, yeah, you kids have it so easy. All right, so I'm going to repeat this again. So the NMR spectrometer will automatically calculate and plot it and give you a ratio. For number of hydrogen. But is not the absolute number. It's a ratio for number of hydrogen. So it's a ratio for a number of hydrogen. And we call this integration. So far so good. And we call this integration. I want to go over this one more time because I need to make sure you really, really understand this. So here is the deal. So what we're calling right now, we're calling integration. And what is the integration? Integration is basically the ratio between the hydrogen. Is the ratios between the hydrogens, okay? Is not an absolute. Is not absolute. Is just a ratio. Okay? And they're kind of approximate, so sometimes you have to round up and down. So integration, those are ratios, they're not absolute, and then they're approximate, so sometimes you have to round it up and down. And that gives you the ratio for number of hydrogen. So far, so good. Okay. Now, I want to give you an example so you know what I'm talking about, because what I mean by ratios and not absolute and they're approximate, what does that mean? Let's say this is my NMR, okay? And then there we go. Okay, I like this example. So remember what we talked about. We said integration is kind of like the height of the peak is proportional to the area under, and that is proportional to the number of hydrogen. So again, NMR spectrometer is going to automatically calculate it and plot it for me, and it's going to give me a ratio. Now, when I get my spectrum, let's say the NMR is going to tell me 9.2 and 2.8. Okay? So these are the integration that the NMR spectrometer is going to give me. Now, you have to play around with it a little bit. You know what I said? I said they're approximate. You can round up and down. So when I say 2.8 and 9, I'm going to say, okay, probably what we're talking about. We're talking about 3 hydrogen and 9 hydrogen. But remember what I said? I said they're not absolute. They're kind of ratio. So they could also be 1 hydrogen and 3 hydrogen, because they could also just be a ratio and not absolute. So far, so good? Okay, I'm going to go over this one more time. Just want to make sure you're all on the same page. So when you get an NMR is going to give you an integration. Here it gives you really nice integration. When you actually do it, they're never this nice, beautiful numbers. So here's an example. I did an NMR. The NMR spectrometer gave me these numbers, 9.2, 2.8. You play around with it. They're approximate. So probably this is, I can round it to 3 hydrogen and then 9 hydrogen. But again, this is not absolute. It could also be 1 hydrogen and 3 hydrogen. Because again, these are ratios. They're not absolute numbers. Okay? All right. Now the last thing I want to write down before I go to the next one. Again, what integration is basically the number of hydrogen for each peak. So it's a number of hydrogen for each peak. And that's key. So integration is number of hydrogen for each peak, but the numbers that the NMR spectrometer gives you, they're the ratio, they're not absolute, and they're approximate. So sometimes you have to round it. And again, the ratio, so this could be 3 and 9, or it could be 1 and 3. Then you have to like play around with it with your formula to figure it out. So far so good? Okay, so tell me, what does integration mean again? Integration is basically number of hydrogen for each peak. So when you come over here, this peak over here has 3 hydrogen, this one has 3 hydrogen, this one has 2 hydrogen. All right, beautiful. Now, before we go over the last part of NMR, let's do a practice problem. What do you think? Yes, to make sure you have been paying attention to me and not just pausing me and watching something else. Here is a compound. Okay, let me give us, here is a compound. Now, here's what I want you to do. You ready? You're going to pause me. You're going to do this problem and then unpause me so we can go over it. I want you to know if this is my compound and if I take an NMR of this, how many peaks would show up on an NMR spectrum? Okay, how many peaks is going to show up on an NMR spectrum? What is the chemical shifts? What are the chemical shifts for those peaks? And what is the integration? What are going to be the integration for that peak? Okay, so how many peaks? What are going to be the chemical shifts? And what is going to be the integration? Yeah? All right, give this a shot. Now, let's go over it together. First of all, how many peaks is it going to show up on an NMR spectrum? Remember, I did a lecture a little while ago about NMR, and what I said was that NMR, we're going to have a peak for each unique set of hydrogens, right? For each unique set of protons, you are going to have a peak. Now, let's go over here to see what are the unique sets of protons. Okay, so one thing that really helps me is actually drawing the hydrogens out. There's 3 hydrogens here, there's 2 hydrogens here, and there are 3 hydrogens here. So far so good? Okay. Now, these 3 hydrogens, they are attached to the same carbon, right? So what I'm going to get, there is a unique set of protons right here. And I'm going to call it A. Okay. Now again, NMR, proton NMR, we're looking for hydrogens. All we're looking for hydrogens. All right. There's no hydrogens here, no hydrogens here. Now let's come over here. These 2 hydrogens are attached to the same carbon, right? Now, this is another set of unique protons. Okay. Now, how about this one right here? Yeah, these 3 are equivalent to each other. They're attached to the same carbon, right? Okay. This is another set of unique protons. You follow me so far? Okay. So how many peaks is going to show up on an NMR? On an NMR, we are going to have 3 peaks. Now, I want to repeat this again. I know you're probably going to be mad at me repeating myself. I want to do it again. Remember, you have a peak for each unique set of protons. For each unique set of protons, you are going to have a peak on an NMR. Now, this is unique. These hydrogen are attached to the same carbon, and this carbon is attached to a carbonyl. This is unique. Now, these 2 are attached to the same carbon, and this carbon is attached to an oxygen that is attached to a methyl. Now, these ones also unique. This CH3 is attached to a CH2. So each one, those are unique sets of protons. So 3 peaks is what's going to happen on a NMR spectrum. So far so good. You following me? Beautiful. Okay. So number 1, we know we're expecting to see 3 peaks on our NMR spectrum. Number 2, now the chemical shifts. Remember, I gave you a little handout and I'm going over that handout. So take advantage of that. Over here. So again, remember what we talked about. We have unique hydrogens over here, here, and here, right? Okay, now here, these hydrogens are attached to a carbon, and this carbon is attached to a carbonyl. Do you guys remember this? So if you go back over here, when the carbon bonded to hydrogen is not directly attached to an oxygen, is going to be lower ppm, but here is not directly attached to an oxygen, but the carbon is attached to a carbonyl, and that's going to end up about 2 ppm. So far so good. So again, the carbon is not directly attached to an oxygen, but the carbon is attached to a carbonyl. Okay, so the carbon bonded to the hydrogen is attached to a carbonyl. That means it's going to show up at around 2 ppm. That's exactly the case here. This carbon is not directly attached to an oxygen, but this carbon is attached to a carbonyl. So what's going to happen here, we're going to have a peak around 2 ppm. So far so good. Okay. How about over here? What do you think? Now, the carbon attached to these hydrogens is directly attached to an oxygen, right? So if you directly attach to an oxygen, you're going to be more downfield. So this is going to be around 4 ppm. Okay, you guys are going to be good so far? So again, if I have a carbon bonded to the hydrogen, if it's directly attached to an electronegative atom like oxygen, it's going to be around 4 ppm. But carbon bonded to the hydrogen, if it's attached to a carbonyl, that's about 2 ppm. Not so bad, right? Yeah, you guys are doing well. Alright, how about C? Okay, the C is about what? It's a CH3 attached to a CH2 and then attached to an oxygen. I want to say this is probably around 1 ppm, right? It's probably around 1 ppm. You can see over here, let's come over here. Again, it's just a CH3 attached to a CH2, right? But there is that oxygen nearby, so I'm going to say it's probably around 1 ppm. So right here, CH3 attached to one carbon, but again, that one carbon is attached to oxygen, so maybe like around 1, maybe 1.1. That's where I would expect the chemical shift to show up. So far, so good? Okay. Beautiful job. Beautiful job. All right, so that's not bad. You know how many peaks you're expecting. You know the chemical shifts. Now, the next thing to do is integration, right? We're going to go over integration. Okay. So, what kind of integration you expect? And remember what we talked about integration is number of hydrogen for each peak. So, I know I have a 3 peak. I have a peak here, I have a peak for here, and I have a peak for here. Now, what's going to be the integration for each peak? Now, this one right here, for A, I'm going to end up with 3 hydrogen for that peak. For B, it's a CH2. I'm going to end up with 2 hydrogen for that peak. And then for C, I end up with 3 hydrogen for that peak, right? Because again, I have 3 hydrogen, I have 2 hydrogen, and I have 3 hydrogen. And again, integration is number of hydrogen for each peak. I know this peak is supposed to have 3 hydrogen. I know this peak should have 2 hydrogen. And I know this peak should have 3 hydrogen. Yeah? Okay. Nice job. Very nice job. All right. So hopefully this will give you a little practice. Now let's go over the last part of NMR. So we've gone over chemical shifts, integration, and the last one, it sounds funny, spin-spin splitting. Spin-spin splitting. Sounds kind of cool, right? Alright, SSS. Let's learn about spin-spin splitting. Okay, now let's go back to our sample NMR. Over here, pay attention to this. So we had 1, 2, 3 peaks. And peak 1 had an integration of 3 hydrogen, then 3 hydrogen, then 2 hydrogen. And then you had the chemical shift about 1.1 ppm, 2 ppm, about 4.1 ppm. And then you had the chemical shift. So we had the integration and we had the chemical shift. Now when you look over here, there is something else interesting about these peaks. What stands out to you? Look at these 3 peaks. What stands out to you? Yeah, you probably are asking me right now, even though I can't hear you, that how come this peak has 3 lines, this peak has 1 line, and this peak has 4 lines? What's going on there? This has 3 lines, we call it a triplet. This one has a single line, so we call it a singlet. And this one has 4 lines, we call it a quartet. So what is going on there? Well, that's spin-spin splitting. So that's the last thing we're going to talk about NMR. So far, so good? Okay, so these are spin-spin splitting, triplet, singlet, and I have a quartet. Okay, let's go over what is spin-spin splitting. So again, like we said, the peaks, we have a singlet, we have a doublet, we can have a triplet, we have a quartet. Now let's talk about why is that? Why is that? How do they rise like that? We are going to talk about N+1 rule, which help us understand the spin-spin splitting. N+1 rule. You ready? Okay. Here is the rule. I'm gonna write down the definition. I'm gonna write down the rule, and then we're gonna go over it. So I'm gonna write it down. I'm gonna be a little bit confused, but don't worry, I will explain it. It's basically number of hydrogen on the adjacent carbon or the same carbon that are equivalent to each other but non-equivalent to the hydrogen that we are looking at. Yep, I can imagine your expression right now, like, what the heck, what does that mean? Don't worry, we're going to go over it. I just want to put down the rule. So number of hydrogen on an adjacent carbon or the same carbon that are equivalent to each other but non-equivalent to the hydrogen that we are looking at. And that is my N. This is my N. Yeah, this makes perfect sense, doesn't it? No. We're going to go over this. To figure out the N. We actually do a lot of practice problems to make sure we get this down. Now, the best way to teach you this is start drawing the compound, and then we can go over how this N+1 will work, and then how do you get the N. Let's say that we are looking at these hydrogen over here, okay? These are our absorbing hydrogen. So we are looking at these hydrogen over here. This is my absorbing hydrogen, okay? All right. So the N is number of hydrogen on an adjacent carbon or the same carbon that are equivalent to each other but not equivalent to the hydrogen we're looking at. So we're looking at this hydrogen over here, right? Now let's look at the adjacent carbon. Again, these are on this carbon. These hydrogen are on this carbon. We're going to look at adjacent to this carbon. This side, we have a Br. You know what I'm actually going to do? I want to circle this whole thing to make it a little bit more interesting. So, these are the hydrogens we're looking at, and they're attached to this carbon. So, these are the hydrogen we're looking at. These are our absorbing hydrogen. Now, let's look at the adjacent carbon. The adjacent carbon over here has one hydrogen, and over here there is no adjacent carbon. You guys are good so far? Okay. So number of hydrogen on adjacent carbon or the same carbon that are equivalent to each other but non-equivalent to the hydrogen that we're looking at. Well, what does this mean? these two hydrogen are equivalent to each other, right? This is one peak that we have. Now, adjacent here, we have no carbon that has no hydrogen. And over here, the adjacent carbon has one hydrogen. Okay? So what that means is this hydrogen is looking at this hydrogen over here. So what is my N value here? My N value is 1 because the adjacent carbon has only one hydrogen. The adjacent carbon has only one hydrogen. Yeah? Okay. So, N plus 1. N is 1 plus 1. It would be 2. So what we're going to have, we are going to have a doublet. It's going to have 2 lines when we have this peak. So far, so good? Okay. Now, I want to go a little bit more in depth of why this is a doublet. Okay? I want to go a little bit in depth why this is a doublet. So I'm going to expect a doublet, 2 lines on a spectrum for this peak. And the reason is because the adjacent carbon has one hydrogen. N plus 1 rule, 1 plus 1 would be 2. Now, let's get a little bit, take a closer look at what's going on. And if you're confused right now, don't worry. You won't be by the time I do our 100th problem. Okay? So don't worry just yet. Okay, let's take a step back. I'm going to look at this again. So again, we are looking at what kind of peak we expect for this. A singlet peak, a doublet peak, a triplet peak, a quartet peak. What kind of peak we expect for this? Okay. Now this peak has only one neighbor. Do you agree? This carbon has only one hydrogen, and over here there is no carbon with hydrogen. So this one has only one neighbor. I'm actually going to write this down. So here is the peaks we're looking at. We're going to expect what kind of peak we expect. This one has one neighbor. It has one neighbor. Okay? And I'm going to call this HA. It has one neighbor. I'm going to call it HA. Now, here's the thing. The neighbor could be aligned with the magnetic field, or it could be against the magnetic field. Remember that? We said they're either aligned with the magnetic field, or it could be against the magnetic field. So these hydrogen, these absorbing hydrogen, they feel to a slightly different magnetic field. One could be aligned with it, or it could be against it. So they feel two slightly different magnetic field. And that's why it's going to absorb 2 different frequencies, and we are going to have a doublet. I'm going to explain this again. So again, we're looking at the neighbor. So these are my hydrogen. These are the hydrogen that I'm looking at. I want to see what I'm expecting. This hydrogen has only one neighbor, right? And that is HA. And if you remember, we said the HA sometimes they could be with the magnetic field, or they could be against the magnetic field. So this absorbing hydrogen is going to feel 2 slightly different magnetic field. And that means is going to absorb 2 different frequency. So I'm going to have a doublet. So far, so good. Okay. Now, when you have a doublet, and I sort of draw it out here, let me draw a little bit nicer one. So I'm going to have a doublet. The distance between these two matter. What we call that? We call that a coupling constant. We call it a coupling constant. Basically, it's a frequency difference between these two. And it could be between 0 to 18 hertz between the peaks. Okay? So, you know that we're going to have a doublet because this one has one neighbor, n plus 1 rule. It has one neighbor, so my n is 1. 1 plus 1 is a doublet. This is what I need you to know. And then I want you to even know a little bit more about these things, because sometimes when you know more, it makes more sense. So this one has one neighbor. This is the neighbor. I'm going to call it HA. Now, we knew what we talked about. We said they could be with the magnetic field or they could be against the magnetic field. So it's feeling two slightly different magnetic field is going to absorb two different frequency. So I'm going to have a double it for a peak. Now, the distance between these two, we call that a coupling constant, is a frequency difference between those. And it's usually between 0 to 18 hertz. All right, beautiful job. Ready for our next practice problem? Here is our next practice problem. I'm going to keep doing this until you understand spin-spin splitting really well. Sounds cool, right? Okay. Here is our next one. One I'm interested in is this hydrogen right here. That is my absorbing hydrogen. I want to know what kind of peak should I expect for this? What kind of peak should I expect for this? Okay. All right. I'm going to look at the adjacent carbon. So this hydrogen is attached to this carbon. And we're looking at this one to see what kind of peak we're going to expect. Adjacent carbon, here there's one adjacent carbon and it has what? It has two hydrogen. So I have A and B, that's that one adjacent. And then this one, it has no hydrogen. Okay? So the adjacent carbon has how many N+1 rule? The adjacent carbon has how many hydrogen? The adjacent carbon has two hydrogen, right? So it would be 2 plus 1, it would be 3. So what do I expect? I expect a triplet. Let's go over this again. This is the peak I'm looking at. I want to know what type of peak should I expect. You have to look at the adjacent carbon. So there's no carbon over here. The adjacent carbon over here, there are two peaks. 1, 2. N+1, 2 plus 1 would be 3, would be a triplet. Yeah, this would be a triplet. Okay, now I'm going to draw the triplet out. So this is going to be a triplet. This is what we are going to get for NMR. Okay, now let's go over why we are getting a triplet. Okay, let's go over why we are getting a triplet. Again, you don't have to know this, but sometimes knowing a little bit more, it helps to understand what's going on here. Now, we said that the adjacent carbon had two hydrogen, HA and HB. Okay, now here's the deal. HA could be aligned with a magnetic field, and HB could be aligned with a magnetic field. Okay. Now, HA could be against the magnetic field, and HB could be aligned with the magnetic field, or the other way around. HA could be aligned with the magnetic field, and HB could be against the magnetic field. So, one option is both aligned, the other option is one aligned, one is not, and then the last one is A is against the magnetic field and B is against the magnetic field. That's one option here. And this is two options because it could be A down, B up, or it could be A up, B down. Okay. Now this means we're gonna have a triplet. Okay. There's different. What's gonna happen is the hydrogen is gonna feel those three slightly different magnetic fields. So it's going to absorb different frequencies. Now this is 1, now this is 2, it's going to be taller, and this is 1, it's going to be over here. So this is going to be our triplet. This is going to be our triplet. So far so good? Okay, and the distance between these are coupling constant. Yeah? Okay. Ready for next one? We're just going to keep doing this until you get this down. Here is our next problem. I'm going to have a CH3 attached to a carbon that is attached to a Br, attached to a hydrogen, and then it's attached to a CH3. So far so good? Okay. Now here's the first thing I want you to figure out. The first thing I want you to figure out is how many peaks. Let's do practice as we're learning spin splitting. How many peaks do you expect to get on the NMR? How many peaks are we going to have on the NMR spectrum? How many peaks? What do you think? Take a minute, do this, and then we're going to go over it together. How many peaks do we expect on NMR? And again, remember, basically, how many unique set of protons do we have? Let's do it. Over here, these hydrogens are pretty unique, yeah? These are the unique set of protons. Now, this one is a unique set of proton. Do you agree? Okay. Now, how about over here? Is that a unique set of proton? That's actually the same as A, right? And hopefully you see it right away by now. And if you're not there, you will get there. Because, remember, look at the neighbors. Look at the neighbor. So here, these hydrogens, this CH3 is attached to a CH that is attached to a Br that is attached to a hydrogen. This is exactly the same. This CH3 is attached to exactly the same neighbor, right? Is exactly attached to the same neighbor. The other way to look at it, and for people who are really good with symmetry, there is a symmetry going on right here, right? We have a symmetry going on right here. So yes, these two are the equivalent. These two are equivalent. So far, so good. So, how many peaks we expect? We only expect 2 peaks. We only expect 2 peaks. Because the A's, they have the same neighbor, right? That's the way to look at it. They have the same neighbor. All right, beautiful. Now, the next thing we want to solve, we know we get 2 peaks. We want to know what type of peaks, what kind of peaks are we going to get? What is going to be the spin-spin splitting for each peak? Spin-spin splitting for each peak. Ready to do it? Let's do it. Okay. Now, let's look at A first. That's a little bit easier. Now, the adjacent carbon has how many hydrogen? The adjacent carbon has how many hydrogen? The adjacent carbon has only 1 hydrogen. You agree? So the adjacent carbon has 1 hydrogen. So what is my N? My N is 1. 1 plus 1 is going to be 2. That means what I'm going to get? I'm going to get a doublet. So far so good. Because again, you look at the adjacent carbon. Adjacent carbon has 1 hydrogen. So 1 plus 1 is 2. So I'm going to get a doublet. We're good? Okay, beautiful. Now, let's look at peak B. Peak B has 2 adjacent carbon. Do you agree? So peak B has 2 adjacent carbon. Now, what's going on there? Well, how would that change everything? If you look over here, this adjacent carbon has 3 hydrogen. This adjacent carbon also has 3 hydrogen. So what is going to be N plus 1 rule? So adjacent carbon 3 hydrogen, adjacent carbon 3 hydrogen. 3 plus 3 would be 6. So 6 plus 1, you're going to get a 7. What is that? That's a heptet. Or some people call it septet, right? That's a heptet, or we can also call it a septet. You're going to have 7 lines for that peak. But when it goes more than 5, we usually just call it a multiplet. We usually just call it a multiplet. So when it goes like more than 5 or 6, we just call it a multiplet. So what do I expect? I expect a doublet and I expect a multiplet for the 2 peaks of the NMR. Now, I want to go back to this because this is actually a very interesting problem. So the adjacent carbon, I have 2 adjacent carbon, right? I have 2 adjacent carbon. This one has 3 hydrogen. This one has 3 hydrogen. I added them together. I said, okay, this peak is going to have 6 neighboring plus 1. That would be 7. I could add them up together. It's okay to add them up together because these two are equivalent to each other. So what I did, I added them together. It's okay to add it together because those are equivalent to each other. Because do you agree that this one and this one, these are equivalent to each other, right? We're going to get 1 peak for those. Because they're equivalent to each other, I can just add them together. So the neighboring would be 1, 2, 3, 4, 5, 6. Because these two are equivalent to each other. Now I know I keep repeating that because if you go back here, number of hydrogen on an adjacent carbon or the same carbon that are equivalent to each other but non-equivalent to the hydrogen that we're looking at. So these hydrogens are not equivalent to the hydrogen we're looking at, but these hydrogens are equivalent to each other. So then it would be 6 plus 1, that would be a multiplet. So we're going to have 2 peaks. We're going to have 2 peaks. One of them is going to be a doublet, and the other one is going to be a multiplet. When it's more than 6 and 5, we just call it a multiplet. Yeah? Okay. Ready for the next one. We're just going to keep doing this. Here is the next problem. I'm going to have a Cl, CH2, CH2, and Br. Okay? Now, first of all, how many peaks do you expect to show up on NMR? What do you think? How many peaks do you expect to show up on NMR? Basically, how many unique sets of protons do we have? Hopefully you're saying 2, right? This is a unique set and this is a unique set. Again, this is a CH2 attached to a CH2. This is a CH2 attached to a CH2. But this CH2 is attached to a Cl versus this CH2 is attached to Br. So 2 unique peaks is what we are looking for. Alright, so far so good. Now, let's come over here. Let's look at A. A, again, the n plus 1 rule, right? The n plus 1 rule. You have to look at the adjacent carbon. So, right here, there's no carbon over here. This carbon has how many? It has 2, right? So, it would be 1 plus 2 would be a triplet. Now, how about for this one? Exactly the same thing. So, this was for HA. Now, let's go for the HBs. Exactly the same thing. So that here, there's no carbon here. There's no carbon with hydrogen. On the left side, there are 2 hydrogen on the adjacent carbon. Okay? All right. So what do we expect? What do we expect? What we would expect for this unique peak, we would get a triplet. And for this peak, we would get another triplet. So far, so good. Okay, again, I know by looking at this, I have 2 sets of unique protons. Once I figure it out, and I need to figure out what type of peak am I going to get. What is going to be spin-spin splitting? It's kind of fun to say it. You have to look at the adjacent carbon. And each one has 1 adjacent carbon that has 2 hydrogens. So 1 plus 2 would be a triplet. Sounds good? Okay. Basically, the HA is going to be split into a triplet by HB, and HB is going to be split into a triplet by HA. Ready for next one? Let's do it. You know what? I think this is it for today. We have done a lot of practice problem, and I think I want to give you a break to kind of get used to everything we've talked about, and then we'll do more practice problem next time. Today was a big lecture. I feel like right now you deserve to go get ice cream. I will talk to you guys next time.